In this video, we will apply what we've learned about molecular orbital theory to understand the phenomena of aromaticity and to analyze aromatic molecules. We're going to warm up before we even take a look at our learning goals, because in order to analyze aromatic molecules, we will need to be able to identify conjugated pi systems and count the number of pi electrons in those systems. So pause and please answer the questions for these two molecules. In the first molecule, there are two pi systems. They are not connected to one another, though in each of them there is conjugation of p orbitals on the atoms that I'm highlighting. Okay, but these are two separate pi systems. In each of these pi systems, there are 6 pi electrons. 2, 4, 6. 2, 4, 6. Those intervening sp3 hybridized carbons disrupt this entire molecule being fully conjugated, so it's not. There are two separate pi systems. Let's take a look at the second molecule here. The second molecule also has a conjugated pi system. I think identifying that these 4 atoms are involved in it is fairly straightforward. We can see those pi bonds. We know pi bonds are made from p orbitals, so we feel pretty good that those 4 atoms are involved in a conjugated pi system. Take a look at nitrogen. Hopefully alarm bells are going off in your head. There's a lone pair of electrons adjacent to pi orbitals. What does that mean? Well, that means that if this lone pair is in a p orbital, it can be shared among all the atoms in the ring. All right, in other words, a conjugated pi system could be formed. And we know that conjugation lowers the energy of electrons. Thus, this nitrogen is sp2 hybridized, meaning that all of the non-hydrogen atoms here are in the same plane. This nitrogen is sp2 hybridized trigonal planar. That accommodates that lone pair being shared in the pi system. That's a lot. It's very conceptual. If we're not quite there yet for how we are considering these problems, I think that we can all recognize that this molecule can be described by resonance structures. And in a valid resonance structure, we can see that nitrogen is making a pi bond. Thus, it must be sp2 hybridized because pi bonds are made from p orbitals. If nitrogen is making a pi bond, it must have a p orbital. Thus, it is sp2 hybridized, and that lone pair, what looks like a lone pair in the dominant Lewis structure, is actually not a lone pair. It's actually in a pi molecular orbital spread out around the entire ring. Okay, so there's 2, 4, 6 electrons in this 5 atom, 1, 2, 3, 4, 5 atom pi system. Excellent. Once you feel comfortable with these two examples, you are ready to move on to learn about aromaticity and aromatic molecules. Our learning goals for today include identifying an aromatic, anti-aromatic, or non-aromatic ring, explaining with molecular orbital theory why aromatic compounds are so stable while anti-aromatic compounds are unstable. Well, we might not know what that means, but if aromatic compounds are so stable, they must be low energy. If anti-aromatic compounds are unstable, they must be high energy. Cool. We want to draw the pi molecular orbitals for benzene. We're getting really good at this now. I'm sure we'll have no problem. And then this is a bit boring, but we want to be able to provide systematic names for benzene derivatives. So some of this you might learn on your own with the use of a textbook. It's not something that you need to hear me explain. You just got to follow the rules, but we'll get to that at the end. All right, let's get started. So I have a question for you, and I will say we're not going to fully answer this question today. Nevertheless, we will start to think about this question. So go ahead and write something down. Which molecules that make up your body or interact with your body need to be particularly stable to support life as we know it? These types of questions are always fun. Although I'm not with you, I don't know what you wrote down. Common answers are water. DNA is another common answer. Others, you may have come up with other molecules that should be stable to support life. So we'll come back to this question. I would now like for you to predict the product or products of this reaction. Pause and do that. When we're problem solving, we always identify functional groups and ask reagents what they are. Are they electron rich, electron poor, acid, base, etc.? There's an arene, an aromatic ring, consisting of these three adjacent pi bonds. There's an alkene. And then you might actually notice something here. The alkene and the arene for this particular molecule, they're conjugated, they're connected. Each adjacent atom has a p orbital with which it's making a pi bond. And if all 8 of those p orbitals are aligned, they certainly do all overlap. Now why? Because when the 8 orbitals overlap, they make 8 new lower energy molecular orbitals. So in most cases, the more orbitals that overlap, the lower energy the electrons will be. Thus, it happens, right? The universe spontaneously goes to lower energy. Conjugation results in lower energy orbitals. And since electrons occupy orbitals, conjugation results in lower energy electrons. So there's an arene and an alkene, and they are conjugated to one another, which will affect their reactivity under some conditions. There's molecular bromine, and we may recall that molecular bromine reacts with alkenes via an electrophilic addition reaction. This can be a bit confusing. Electrophilic additions are classes of reactions, just like substitutions are classes of reactions. They can proceed by more than one mechanism. And then there's also electrophile addition, which is an elementary step that we learned that organic molecules can undergo. So I'm sorry those two very similar terms can be a bit confusing. So alkene is converted to a 1,2 dibromide, also known as a vicinal dibromide. Vicinal means the two functional groups are on adjacent carbons. They are neighbors. They're in the vicinity of one another. So we might wonder, okay, does every single pi bond in this molecule react with bromine? And perhaps you know the answer. The answer is no. The aromatic ring does not react. It's only the alkene functional group that reacts. This is a chiral product and it's formed as a racemic mixture. Addition can happen to either face. Ooh, we have a nice diagram up here. Let's look at that. So the electrophile, bromine, can either add to the top face of the alkene, or it could have added to the bottom face of the alkene. Those two faces are exactly the same. So that will result, adding to the top face results in the bromine being up. Adding to the bottom face would result in the enantiomer, which I haven't drawn here, but we certainly can, with bromine behind the plane of the screen. Both of these attacks are equally likely, and so these two enantiomers are formed in a 50-50 mixture. That's what this plus minus means. It means a racemic mixture of two enantiomers, a 50-50 mixture of two enantiomers. That's a fun review. What is most important and notable today is the observation that the arene did not react. Aromatic rings are typically, under the normal conditions that we have learned for reactions of alkenes, aromatic rings are unreactive. We can conclude from that aromatic rings are stable. And if we're unsure of whether or not we can conclude that, we could put a question mark. This could be an inquiry question. Okay, so the bottom line was this molecule here actually has a name. It's called styrene, where you have the alkene attached to the phenyl benzene ring. When styrene reacts with molecular bromine, or under any of the conditions that we learned in Organic Chemistry 1 for reactions of alkenes, only the alkene portion reacts, not the aromatic ring. We're concluding from that observation that aromatic rings are stable. Let's move on to some definitions. Well, your neighbor is probably not in the same room as you, but feel free to text a friend or just take a quiet moment and define these terms. Define them and give an example of each of these terms and give an example of a molecule that can be described by each of these terms. Do you have something written down? Okay, we'll see. Let's start with aromaticity. Benzene is the prototypical aromatic compound. When you were introduced to aromatic ring or arene as a functional group, you learned to memorize benzene. However, benzene is only one example of an aromatic compound. The criteria for possessing the property of aromaticity are that the molecule must contain a contiguous, planar, and cyclic arrangement of p orbitals. That is indeed the case for benzene. Each of the carbon atoms in benzene is sp2 hybridized, meaning that each of those atoms possesses a p orbital. Those p orbitals are all aligned. Contiguous, each adjacent carbon contains a p orbital. Planar, all 6 atoms occupy the same plane, which means that all 6 p orbitals are aligned and can overlap. Cyclic, this occurs within a ring. This arrangement of p orbitals is not enough for a molecule to possess aromaticity. The cyclic pi system of that molecule must contain 4n plus 2 electrons, where n may be 0, 1, 2, etc., so any integer. For example, when n equals 0, 4n plus 2 is 2. When n equals 1, 4n plus 2 is 6. When n equals 2, 4n plus 2 is 10 electrons. Benzene contains 6 pi electrons, 2, 4, 6, in a contiguous, planar, and cyclic arrangement of p orbitals. Thus, it is aromatic. And as we have learned and observed and will continue to observe, aromatic compounds are particularly stable. Recall the reactivity of styrene. The aromatic ring did not react under conditions by which normal alkenes do react. That's cool. I hope we can also understand why aromatic compounds are particularly stable. I bet we will, and I bet we'll use molecular orbital theory. Okay, so we've defined aromatic. Pause, go back, and write a definition in your own words and give an example. Benzene, that's the prototypical aromatic compound. So aromatic compounds are particularly stable. Conversely, a contiguous, planar, and cyclic arrangement, like this, of p orbitals that contains not 4n plus 2, but 4n pi electrons, is anti-aromatic. And anti-aromatic compounds are particularly unstable, whereas aromatic compounds are low energy, stable. Anti-aromatic compounds are high energy, unstable. If benzene is the prototypical aromatic compound, perhaps cyclobutadiene is the prototypical anti-aromatic compound. Each carbon atom of cyclobutadiene is sp2 hybridized in this drawing. Thus, each of the 4 atoms in cyclobutadiene has a p orbital, right? sp2 hybridization results in 3 sp2 orbitals that make the sigma bonds. So 1 sigma bond, 2 sigma bond, 3 sigma bonds. And then the leftover p orbital makes pi bonds. So each of those atoms has a p orbital. Those p orbitals could be aligned if the 4 atoms are coplanar, and thus cyclobutadiene would have a contiguous, planar, and cyclic arrangement of p orbitals. But unlike an aromatic compound containing 4n plus 2 electrons, Anti-aromatic arrangements of p orbitals contain 4n electrons. Again, where n is any integer. For cyclobutadiene, the 4 pi electrons, 2, 4, are an example of 4n electrons. Thus, cyclobutadiene is anti-aromatic. Well, now you can define anti-aromatic. You write down the words, and here's an example. As we noted, benzene is just the prototypical aromatic compound, but there are many, many compounds that possess the property of aromaticity. Cyclobutadiene is simply one example of an anti-aromatic compound. There are many compounds that have the potential to be anti-aromatic. Let's now practice identifying whether or not compounds are aromatic, anti-aromatic, or non-aromatic, which means neither aromatic nor anti-aromatic. Before this exercise, we should be sure that we understand the definitions of aromatic and anti-aromatic, as well as non-aromatic. So both aromatic and anti-aromatic should contain cyclic, planar, contiguous arrangements of p orbitals. Aromatic compounds will possess 4n plus 2 pi electrons in that system, whereas anti-aromatic compounds will possess 4n pi electrons in that system of cyclic, planar, and contiguous p orbitals. Aromatic and anti-aromatic compounds are examples of conjugated pi systems, just very particular conjugated pi systems. Thus, we can begin with our skills of identifying which atoms and how many electrons are in various conjugated pi systems. So go ahead and do that now. Examining the first molecule on the left, which has the common name furan, we realize that oxygen is sp2 hybridized. If it is sp2 hybridized, it has 3 sp2 orbitals and 1 leftover p orbital with which it can make pi interactions. That would put one of these pairs of electrons in a p orbital, meaning it would be conjugated with the p orbitals on the 4 carbon atoms, and thus this molecule would be described by resonance structures, meaning the conjugation and delocalization of electrons would occur. Conjugation and delocalization of electrons leads to lower energy orbitals in almost every case. Thus, we do expect that oxygen to be sp2 hybridized, having that p orbital. So furan could be represented by 5 atoms with p orbitals. If all 5 of those atoms occupy the same plane, furan will have this cyclic, planar, and contiguous arrangement of p orbitals. When we count the electrons in the pi system, we count 2, 4, and the 2 double bonds, 6. So one of the lone pairs of oxygen is involved in the pi system. The other pair of electrons occupies an sp2 orbital. Thus, furan has 6 pi electrons in that cyclic, planar, and contiguous arrangement of p orbitals. 6 pi electrons is 4n plus 2, where n equals 2. Thus, furan is aromatic, and we expect it to be stable. The next compound, cyclohexyl-1,4-diene, does possess a conjugated pi system, but the system of p orbitals is not fully cyclic because there are these 2 sp3 hybridized carbons that do not have p orbitals and thus break up the pi system. Because the pi system is not fully cyclic, this compound is non-aromatic. And it doesn't matter how many electrons are in that pi system, it's still just non-aromatic. It doesn't have a fully cyclic arrangement of p orbitals. In the next example, we again see a lone pair of electron adjacent to pi bonds. That suggests to us that this molecule could be represented by resonance structures. In that case, these 2, 4, 6, 8 pi electrons do occupy a fully cyclic, planar, contiguous system of p orbitals. 8 pi electrons is 4n, where n equals 2. So we expect this molecule to not be particularly stable, as it represents an anti-aromatic system. We have already described cyclobutadiene with those 2 adjacent pi bonds. Might be described by resonance. There are 4 pi electrons. 4 pi electrons is 4n, where n equals 1. Each of the 4 atoms of cyclobutadiene is sp2 hybridized, meaning it does have a p orbital, and those p orbitals represent a cyclic, contiguous, and planar arrangement. Cyclobutadiene is an anti-aromatic compound, and we predict it to be particularly unstable. The final example that we will examine at this moment is the cyclopropenyl cation. These 2 carbons are certainly expected to be sp2 hybridized, making a pi bond with p orbitals. This carbon is also sp2 hybridized, and we expect it to have an empty p orbital, hence the carbocation. Thus, all 3 of these atoms have p orbitals that are in a cyclic, planar, and contiguous arrangement. Counting the number of pi electrons, there are 2 pi electrons in this system. 2 pi electrons represents 4n plus 2, where n equals 0. Thus, the cyclopropenyl cation is expected to possess aromatic properties and be pretty stable, especially for a cation. Be sure that you are able to identify whether or not a compound is aromatic, anti-aromatic, or non-aromatic, given the criteria that describe each type of compound. All right, we said aromatic compounds are particularly stable, but so far our only piece of evidence has been the fact that they don't really react. So we saw in the bromination reaction of styrene that only the alkene portion, not the arene ring, reacted with bromine. We can now examine another piece of evidence of the amazing stability of aromatic rings. We're going to use heats of hydrogenation again. So again, taking alkenes and adding hydrogen gas to them. And then the amount of heat released informs us about the initial stability of the alkene. The less exothermic, the more stable or lower energy the initial alkene was. So this is a fun exercise that I had for in-person class, and we can try it via the video as well. I'm sure it'll work great. So we can look at cyclohexene, just this first line here, and its heat of hydrogenation is negative 120 kilojoules per mole. 1,3-cyclohexadiene contains 2 alkenes, so you might expect it to have a heat of hydrogenation of twice that of cyclohexene, but that's not the case. It has a heat of hydrogenation of negative 231, so those 9 kilojoules per mole are just stability that the 1,3-cyclohexadiene has due to conjugation. So 9 kilojoules per mole stability just due to conjugation. Cool. All right, now we can think about benzene, where we're adding one more alkene. Benzene, 3 double bonds. If there's no special stability due to conjugation or due to aromaticity, we might expect a heat of hydrogenation of negative 360, right? That's 3 times the heat of hydrogenation of cyclohexene. Cyclohexene has 1 double bond, benzene has 3. 1,3,5-hexatriene. So maybe we expect something similar, so about 360, except, we know they're conjugated, and we saw there was 9 kilojoules per mole stability due to conjugation and the 1,3-cyclohexadiene. So perhaps instead of just 2 conjugated pi bonds, there's 3. Maybe that'll give us 20 kilojoules per mole stability. So maybe it's negative 340 kilojoules per mole, maybe. What we'll do next is look at the actual heats of hydrogenation data. But let me just be sure that we're all on the same page before we do. We're using cyclohexene as a benchmark. It has an isolated double bond. We've already examined going from cyclohexene to cyclohexadiene. It's not as simple as going from 1 to 2 isolated double bonds. The double bonds in 1,3-cyclohexadiene are not isolated. These p orbitals are connected, they're conjugated. This is a multi-centered pi system. And thus, instead of having a heat of hydrogenation twice that of 2 isolated double bonds, it's actually less than twice. And that's because 1,3-cyclohexadiene starts out with just 9 kilojoules per mole stability due to just the conjugation of the double bonds, leading to lower energy pi molecular orbitals and thus lower energy electrons. There were 2 new molecules that I asked you to predict the heats of hydrogenation for based on these 2 data points. The first is benzene. So I think we have a hard time predicting what the heat of hydrogenation will be. We can say if benzene acts like 3 isolated double bonds, then we would expect 3 times this negative 120 kilojoules per mole heat of hydrogenation observed for cyclohexene. Now we all know that that's not the case, right? At a minimum, benzene represents 3 conjugated double bonds. So if there was 9 kilojoules per mole for conjugation of just 2 double bonds, maybe there's 18 kilojoules per mole for conjugation of 3. We don't know. But, there's also going to be some stability due to aromaticity. So basically, we don't know. We're going to see. And how low this number is tells us, and by low I mean less negative. So deviation from negative 360. That's going to tell us how significant stability due to aromaticity is. And then we have one more data point here, and this is just 1,3,5-hexatriene. And the reason I have this data point is because, like benzene, there will be 3 conjugated double bonds, but there's no aromaticity. So for benzene, we have 3 conjugated double bonds and aromaticity because it's a fully cyclic and planar arrangement of p orbitals. And for 1,3,5-hexatriene, there's just the 3 conjugated pi bonds. So let's look at the data and examine what these heats of hydrogenation actually are so we can learn about how much stability is gained from conjugation and aromaticity. Let's start with the 1,3,5-hexatriene. So the heat of hydrogenation for that molecule is negative 337 kilojoules per mole. And we want to compare this to 3 times the heat of hydrogenation of cyclohexene, which was negative 120 kilojoules per mole. So that difference in energy between what we'd expect due to 3 isolated double bonds versus what is observed, that difference in energy is 23 kilojoules per mole. And that's about what we expected, 20 kilojoules per mole. Stability that the 1,3,5-triene has due to conjugation of 3 double bonds, so of 6 p orbitals being connected. Now, look at the 1,3,5-hexatriene, look at benzene. Benzene only differs from that in the fact that the pi system is now cyclic, right? There's a bond between the 1 and the 6 carbons. Look at the difference in the heats of hydrogenation. Benzene is about 130 kilojoules per mole more stable than hexa 1,3,5-triene. This stability is simply due to the aromaticity of benzene. It is due to the fact that the 3 conjugated double bonds of benzene are connected in a ring in this cyclic fashion, rather than in the acyclic form of hexa 1,3,5-triene. Now that is amazing, and we will very soon, I hope, understand why aromaticity provides so much stability for the electrons in the pi bonds of benzene. In the meantime, let's take a quick detour. Early chemists were obsessed with benzene. Early chemists knew that the molecular formula of benzene was C6H6. They also knew that benzene was very stable, but they could not quite come up with the structure of benzene. Now, this story is probably false and just told to advance his own self-interest, but in the late 19th century, Kekulé, who was a hydrocarbon chemist, he described a dream that he supposedly had about benzene. He dreamed there was a six-carbon snake chasing its own tail, and he realized in that moment that benzene was a ring of alternating double and single bonds. Or at least that's what Kekulé thought. Kekulé proposed this structure with alternating double and single bonds, and he thought that two isomers would actually be in equilibrium with one another. He proposed that there would be long bonds alternating with short bonds, making up these two isomers. Kekulé's proposed structure was quite controversial. These alternating long and short bonds would suggest that there should be four isomeric dibromobenzenes. And really, the issue is in the 1,2 dibromobenzenes. One isomer should have this short bond if, in fact, Kekulé was correct, and the other isomer should have this long bond between carbons 1 and 2. However, chemists knew that there were not four dibromobenzenes, there were only three. In fact, these two were the same. Kekulé's structure was correct in proposing this ring structure of benzene, but it was incorrect in proposing the two isomeric forms with alternating long and short bonds. Eventually, chemists realized that benzene is best described, as you understand, by two resonance structures. These resonance structures are equivalent, and each of the carbon-carbon bonds has a bond length of 1.43 angstroms. Sometimes benzene is drawn like this to show that all of the carbon-carbon bonds are the same. In fact, there are 6 pi electrons spread out or delocalized over all 6 atoms of the ring. Thus, all those carbon-carbon bonds are the same length. Wonderful. We took the detour and thinking about the funny dream about a snake chasing its own tail. We realized early chemists first proposed the wrong structure for benzene. They proposed that it was a molecule with alternating short and long bonds existing in equilibrium between two isomeric forms. But really, we know no, benzene is best described by two resonance structures. And all the bond lengths are the same because these two resonance structures are equivalent, and the actual molecule is a composite of them. So the actual bond length is somewhere in between a single and a double bond. However, we have not explained why benzene is so stable. I suggest you take a moment and see if you can explain the unusual stability of aromatic molecules such as benzene. Why are aromatic molecules so stable? Well, the answer, of course, is in the energy of the electrons in the pi system. So we will now examine the pi molecular orbitals for benzene. Before I show them to you, let's do a bit of analysis ahead of time. So benzene consists of a 6-carbon conjugated pi system. These 6 p orbitals will combine to form 6 new pi molecular orbitals. And these orbitals will be quite distinct for those that we formed for just this simple 1,3,5 hexatriene. In fact, these 6 new pi molecular orbitals are quite different than what we observed for the cyclic system. Let's examine these molecular orbitals for benzene now. The lowest energy orbital for benzene will have 0 nodes. All of the p orbitals for benzene combine in phase. The next highest energy orbital has 1 node. Now there are 2 degenerate orbitals with 1 node because there are 2 ways to orient that 1 node. It can bisect the ring like this or like this. Then there is the energy of the p orbitals. Then there are 2 antibonding orbitals, each with 2 nodes. The nodes can be distributed like this or like this. And those 2 orbitals are degenerate. They have the same energy. Finally, there is the pi molecular orbital with 3 nodes between each of the atoms of this molecule. Well, nothing looks quite special yet, but it turns out that these orbitals, particularly these bonding orbitals, these are much lower energy than for the acyclic system, such as this system, which we drew in the last lesson. Much lower energy orbitals will result in much lower energy electrons, explaining the special stability of benzene. Benzene contains 6 pi electrons, which will occupy these low energy pi orbitals. Eureka! We've done it! We've explained why benzene is so stable. We have explained the observed 130 kilojoules per mole of stability due to aromaticity from the heats of hydrogenation data, and why benzene is inert, unreactive, under conditions that affect regular alkenes. If the benzene ring reacted, it would no longer be aromatic, and those electrons would no longer have that special stability. We will learn reactions of benzene this semester, but it will require conditions to push the molecule uphill in energy and disrupt the aromaticity. To summarize what we've learned from molecular orbital theory, having the cyclic arrangement of the 6p orbitals results in 1 very low energy orbital with 0 nodes, and then 2 degenerate orbitals with 1 node. Then there are 2 degenerate antibonding orbitals with 2 nodes, and 1 highest energy orbital with 3 nodes. Overall, this results in the 6 pi electrons of benzene occupying quite low energy orbitals. Lower energy, in fact, than the bonding orbitals that result from the acyclic overlap of 6 p orbitals. One more fun fact before we move on. It's hard to tell from my drawings here, which came from my brain and not from a computer modeling quantum mechanics, but this lowest energy pi orbital for benzene, pi 1 here, it is lower energy than actually 4 of the sigma orbitals for benzene. That's remarkable. We've been taught the pi orbitals are higher energy than sigma orbitals, not this pi orbital. This pi orbital, where all 6 p orbitals of benzene combine in phase in this cyclic fashion, it is actually lower energy than 4 of the sigma orbitals for benzene. So not what we would expect based on the usual order of energies of molecular orbitals that we've learned. So that's pretty cool, and I wanted to point that out as well before we move on. You may be amazed or befuddled right now, wondering how we figured out what the 6 pi molecular orbitals of benzene look like, or how to describe them. Well, just like Kekule was obsessed with the skeletal structure of benzene, many chemists have studied benzene, and we haven't mentioned all of their names today. One of their names was Huckel. In fact, Huckel described the 4n plus 2 rule that we learned earlier. Aromatic systems contain 4n plus 2 electrons. Huckel also described the pi molecular orbitals of benzene. Okay, well, we are not physical chemists who are experts in quantum mechanics. So what if we want to draw the molecular orbitals for a cyclic arrangement of p orbitals, aka either an aromatic or anti-aromatic molecule. No problem. Another chemist, Frost, has come to the rescue. Frost described that if one draws a cyclic, fully conjugated molecule with the vertex pointed down and inscribes the polygon in a circle where the vertices intersect the circle, represents the energies of the molecular orbitals. What? Yeah, it was really easy. We're going to be able to do it. Okay, let's figure out what all this means. So thinking about benzene, those carbon-carbon bonds in benzene form a polygon. It's a hexagon. So draw the hexagon with one of the vertices pointing down. In other words, not on its side, which is convenient because I have a very hard time drawing benzene in this orientation. I don't know why. All right, so we're not going to draw it like that. Vertex pointing down. Now we're inscribing the polygon in a circle, meaning drawing a circle around it. Where the vertices intersect the circle represent the relative energies of the orbitals. Oh, we have one lowest energy orbital, and then two degenerate orbitals, two more degenerate orbitals, and then one highest energy orbital. That does look familiar. That does look like what Huckel discovered here. Now, this doesn't tell us how to draw where to put the nodes or how to draw the pictures of the orbitals, and that's actually okay because we don't really need to know what the orbitals look like. We do, however, need to know their relative energies so we can understand why aromatic is stable and anti-aromatic molecules are unstable. We might clean this up a bit. Now let's delete the circle, delete the polygon. All right, there's those 6 MOs. Benzene has 6 pi electrons, which we can put into those orbitals. And there we go. We see, ooh, low energy electrons in benzene, aromatic. Well, what if we wanted to consider a different system? Let's look at the molecules we analyzed a while ago. We predicted that the cyclopropenyl cation would behave like an aromatic compound. There were 2 pi electrons in that fully conjugated cyclic system. Let's examine a 3p orbital cyclic system using a Frost circle to at least figure out the relative energies of the orbitals. Okay. Draw a polygon with the vertex pointed down. Inscribe the polygon in a circle where the vertices intersect the circle represent the orbitals. Just clean it up. Okay, we have 3 orbitals, 3 pi molecular orbitals, which we would expect from 3p orbitals. One orbital is lower energy than a p orbital, so that's bonding. Ooh, and it has 2 antibonding orbitals, which are higher energy than a p orbital. Here are those 2 antibonding orbitals. The cyclopropenyl cation has 2 pi electrons, so whereas benzene had 6 pi electrons, which was 4n plus 2, or n equals 1. The cyclopropenyl cation has 2 pi electrons, which is 4n plus 2, or n equals 0. And those 2 pi electrons occupy that low energy bonding orbital. We can see overall the electrons are stabilized, they're low energy. Thus, this molecule is low energy. Excellent. So now you have the superpower of the Frost circle. If you wanted to examine 5 atom systems or 7 atom systems or 8 atom systems, you could figure out the relative energies of the pi molecular orbitals from these cyclic systems using a Frost circle. And again, you're not going to be able to draw maybe these pictures, but that's okay for analyzing why a molecule is stable or unstable, as long as you know the relative energies of the orbitals. Now that we can explain why aromatic molecules are so stable, the electrons are so stable in the pi molecular orbitals for aromatic systems, let's explain why anti-aromatic molecules are so unstable. We can probably infer that this is because the pi electrons are in high energy molecular orbitals. But we don't have to just infer. We now are armed with the power of the Frost circle and molecular orbital analysis. So let's use it to address this question. You may recall I mentioned cyclobutadiene is the prototypical anti-aromatic molecule. Just like early chemists were obsessed with benzene, which was particularly stable and aromatic, they were obsessed with cyclobutadiene. However, cyclobutadiene did not exist in nature. Chemists theorized that if this molecule existed, it would be quite unstable because it would be anti-aromatic. Well, then, of course, chemists wanted to study it, but in order to study it, they needed to make it. So it took many, many years for chemists to synthesize cyclobutadiene, but under very careful and cold, we're talking about, 30 Kelvin or colder, so super cold, cyclobutadiene has been transiently generated. Transiently, meaning for a moment, and then it reacts. So it's been generated and studied. And bond lengths demonstrate that the double bonds are not conjugated. Cyclobutadiene is made up of alternating long and short bonds. This observation demonstrates that the double bonds are isolated. Cyclobutadiene is not described by resonance structures. Otherwise, we would expect the bonds to have the same length. That's not the case. Why are those double bonds not conjugated? Well, if they were, this system would be anti-aromatic. It would contain 4 pi electrons in a fully conjugated cyclic planar pi system. So chemists certainly confirmed that cyclobutadiene is unstable. You can only make it in a argon matrix at really cold temperatures. But we haven't explained why this 4 pi electrons in the 4 p orbitals represents such a high energy system. Clearly it does. That molecule is really unstable, but why? Well, let's draw a frost circle for cyclobutadiene. Draw the polygon with the vertex pointing down, inscribe it in a circle, clean it up a bit. All right, so we can see there are 4 molecular orbitals. So when the 4 p orbitals of cyclobutadiene combine to make 4 new pi molecular orbitals in this fully cyclic system, the lowest energy orbital is a bonding orbital. Then there are 2 degenerate non-bonding orbitals, and the highest energy orbital is an anti-bonding orbital. It's higher energy than a starting p orbital. All right, doesn't look particularly bad, but let's put in the electrons. So there are 4 pi electrons in cyclobutadiene. 2 of them go into the lowest energy bonding orbital. And then the other 2, one will go in pi 2 and the other will go in pi 3. Uh-oh, do we see it now? Oh, we see 2 things. 2 of these electrons are not stabilized relative to the starting p orbitals. But perhaps more shockingly, cyclobutadiene is actually a diradical. There are 2 unpaired electrons. We might not know exactly what that means, but I bet it causes us to panic. It's worse than a radical. It's a diradical. There are 2 unpaired electrons. So we understand that anti-aromatic molecules are unstable. Aromatic molecules, on the other hand, are quite stable. We've limited our discussion thus far to monocyclic systems, such as benzene and cyclobutadiene. However, there are many polycyclic aromatic hydrocarbons encountered in the lab and in nature. They do have stability due to having aromatic properties, but they're not quite as stable as benzene. For example, naphthalene can be reduced under relatively mild conditions to generate this species. So it is a bit more reactive than benzene. However, you know what, it also does have some stability due to being aromatic. Now, there is some debate over whether or not the Huckel rule, the 4n+2 rule, can be applied to polycyclic aromatic hydrocarbons, but we're going to go ahead and do it. The rule of thumb we're going to use is that if there is a circuit of pi electrons in the polycyclic system, like we see in anthracene, in naphthalene, and in phenanthrene, then we will apply the Huckel rule. In naphthalene, there are 10 pi electrons. In anthracene, there are 14 pi electrons, 2, 4, 6, 8, 10, 12, 14. There are also 14 pi electrons in phenanthrene. 10 electrons represents 4n+2, where n equals 2. 14 pi electrons represents 4n+2, where n equals 3. So again, these polycyclic aromatic compounds do have aromatic qualities, which means they do have some stability relative to acyclic conjugated systems, but they're not as stable as benzene. So benzene is the prototypical aromatic compound. Polycyclic systems can have aromatic properties. And then I did want to point out one more thing. Towards the beginning of the lecture, I asked you to take a look at several compounds and determine whether or not they would have this property of aromaticity. And we looked at a few compounds that contain heteroatoms. So in particular, we looked at furan and this compound with nitrogen. We predicted that furan would have aromatic properties. It has 4n+2 electrons in that cyclic system. And that is the case. Furan is a relatively stable compound. So I would like to explicitly state that heterocycles can also possess aromatic properties, meaning special stability due to that cyclic conjugated pi system. Many aromatic heterocycles are encountered in nature. Hint, hint. Now that we understand what aromaticity is, we will use it to analyze the reactivity of compounds with aromatic properties. Before we do that, let's summarize what we've learned and make some predictions. So aromaticity, containing 4n+2 pi electrons in a fully cyclic contiguous planar arrangement of p orbitals, is low energy. Anti-aromaticity, containing 4n pi electrons in a cyclic contiguous arrangement of p orbitals, is high energy. That's what's meant by stable and unstable. Thus, we can predict that molecules will react to preserve or generate aromaticity. That's just another way of saying they'll react to become lower energy, right, or remain low energy. We can also predict that molecules will react to destroy or avoid anti-aromaticity. There's a little bit of personification there, but you get the point. Avoiding anti-aromaticity just means also, going to lower energy, since anti-aromatic is high energy and anything else pretty much will be lower energy. Let's apply these principles now to a few application problems. We encounter this problem at the beginning of the class. When styrene is treated with bromine, the bromine only adds to the terminal alkene and not the benzene ring. We see the aromaticity of the arene is preserved. Bromine certainly could react with the pi electrons of the aromatic ring. However, this would result in a higher energy species, and the activation barrier is much too high. The species will be higher energy because the aromaticity is lost. So a lot of energy to get uphill. Okay, so it doesn't happen under these conditions. We learned in Organic Chemistry 1 that alkynes behave like alkenes in many electrophilic addition reactions, such as hydration reactions. For example, both alkenes and alkynes react with catalytic acid to undergo hydrations. However, Although alkynes will undergo cyclopropionation with diazomethane, analogous to the conditions under which alkenes undergo cyclopropionation with diazomethane. Alkynes do not undergo epoxidation, which would generate this species called an oxirene and would represent a process analogous to the epoxidation of alkenes under the same conditions, which does occur to form epoxides. Now, it is true that both of these three-membered rings are certainly high energy. They're higher energy than their cyclopropane and epoxide counterparts, just due to increased angle strain. This carbon is sp2 hybridized with an ideal bond angle of 120 degrees, but it's constrained to a 60-degree angle just due to geometry, right? So there's a lot of strain associated with the cyclopropene for sure. And it would also be associated with the oxirene. But the oxirene isn't observed at all, not even a little bit. We can heat this reaction as hot as we want, and the oxirene is not observed. How can we explain this? Well, we're in a class today about aromaticity. So maybe we should pause and analyze both of these rings. These are rings, right? And we should analyze them and determine if they are aromatic, anti-aromatic, or what is the third option? Yeah, the third option is non-aromatic. So apply that skill we developed early on in the lesson. The cyclopropene ring is very strange, but it is non-aromatic. It does not contain a cyclic, contiguous, and planar arrangement of p orbitals, primarily because this carbon is sp3 hybridized and does not have a p orbital. However, oxirene, let's put those lone pairs of electrons on oxygen. If oxygen is sp2 hybridized, and we would expect that it would be, because sp2 hybridization results in a p orbital, and then the electrons in the p orbital would be conjugated, connected to the ring. sp2 hybridization of oxygen does result in a contiguous, cyclic, and planar arrangement of p orbitals. Well, that could be good, right? It could be good if there were 4n plus 2 electrons in this system, but there are 4 pi electrons in this system, 2, 4. Thus, the oxirene would be anti-aromatic. It would be high energy, and that explains why it is not observed. Cool. That was fun. All right, make sure you have that. We've had some fun today learning about the property of aromaticity, but where are we going from here? Well, we learned that benzene is very unreactive, and this is because it is stable. It is low energy. However, it does react under specific conditions. Benzene can be reduced. I mentioned the reduction of naphthalene earlier, and I said that occurred under mild conditions. Of course, reduction under those mild conditions yield a fully aromatic benzene ring, and then a non-aromatic ring where the hydrogen was added. Benzene can also be reduced. 3 equivalents of hydrogen gas can be added across the 3 pi bonds of benzene. I'll just give you an example of one of those equivalents. So each carbon atom starts out with 1 implied hydrogen, and it ends up with 2 implied hydrogen. So there's 1 equivalent of H2, but that happens across each of the 3 pi bonds. So yes, benzene can be reduced, but guess what? It requires 300 psi, that's really high pressure, of hydrogen gas and a special catalyst. So disrupting aromatic systems is uphill. It requires an energy input, but it can be done. It can be done with 300 psi's of hydrogen gas and a special catalyst. No problem, right? A little bit of a problem, yeah. There are some other ways to reduce benzene as well. We'll discuss some later, but they also will involve pretty forcing conditions. Finally, chemists are able to facilitate what's called electrophilic aromatic substitution reactions, where a hydrogen atom can be replaced with some electrophile. This represents a substitution. But just like there was a catch with hydrogenation, there will be a catch with electrophilic aromatic substitution as well. There will need to be either a really, really reactive electrophile to make this process favorable thermodynamically. And you might also notice this electrophilic aromatic substitution, it represents a different pattern than what a normal alkene would do. We know that normal alkenes react with electrophiles to form carbocations, and then some nucleophile in solution can attack them, resulting in an addition product. So for alkenes, we've learned about additions, two atoms adding across the two atoms of the alkene. Whereas for aromatic rings, they're not going to behave just like alkenes. We will not see addition reactions. We'll see substitution reactions. Why do you think that is? Yeah, because the final product has that aromatic pi system preserved. This is just a preview. We will get to it eventually. But for now, we'll spend more time thinking about the phenomena and consequences of aromaticity. Take some time to summarize, write down what you learned today and what questions you still have. And then revisit this question. So think about the molecules that make up your body or interact with your body. Which ones need to be particularly stable for life as we know it? And how do you think that those molecules possess that stability? Perhaps some of them are aromatic. Before we end, let's revisit the learning goals for today. We should be able to identify an aromatic, anti-aromatic, and non-aromatic ring. Non-aromatic rings do not have the fully cyclic arrangement of p orbitals. We've seen several examples where the pi system is disrupted by, say, sp3 hybridized carbons with no p orbitals. Aromatic and anti-aromatic systems will have that fully cyclic conjugated arrangement of p orbitals. The difference is that aromatic systems have 4n plus 2 pi electrons, whereas anti-aromatic have 4n pi electrons. Be sure that you can explain with molecular orbital theory why aromatic compounds are so stable and anti-aromatic compounds are unstable. You can use frost circles to draw the relative energies of orbitals really for any ring size. Put the electrons in, and for aromatic compounds, the electrons were stabilized. They were in those low energy bonding orbitals. And we only looked at the MO diagram for one anti-aromatic compound for cyclobutadiene, but we saw it was a diradical. And that's not evident from the Lewis structure, right? It's only evident when we apply molecular orbital theory. I would like for you to be able to draw the pi molecular orbitals for benzene yourself. You don't need to be able to draw them for any other molecule, but you should be able to draw them for benzene. So spend some time doing that. So it's this picture I'd like for you to be able to reproduce. You can do it. Okay, and then that last learning goal, we didn't even get to it. To be able to provide a systematic name for benzene derivatives, I will provide you with some practice, and we'll continue learning how to name benzene and benzene derivatives as we move forward in the class and learn about the reactivity of benzene later on. This was really fun. I hope that you enjoyed it, and now it's time to practice.